Today we're going to look at exponential functions and their graphs. Let's begin by defining what an exponential function is. An exponential function f with base a is denoted f of x equals a to the power of x, where a is greater than 0, a is not equal to 1, and x is any real number. And these have the distinguished characteristic of rapid growth as x increases. Many real-life applications can be modeled with exponential functions. So what we're going to do is we're just going to plug some stuff into a calculator first to kind of get an idea of how to do that, and then we'll take a look at some graphs. So these first four examples, I've got f of x equals 2 to the x, and I'm going to plug in for x equals negative 3.1. So let me bring in Desmos over here. And we're just going to type in 2 to the x, 2 to the, and then instead of x, we're going to replace that with negative 3.1. So this first one is 0.1166. The second one, 2 to the negative x, I'm just going to do 2 to the negative, and then instead of x, we're going to replace that with pi. So for that one, that's a 0.1133. For the third one, 0.6 to the power of x. So 0.6 to the power of, and then instead of x, we're going to replace that with 3 over 2. That's 0.4647. And the last one, 1.05 to the power of 2 times, and then instead of x, we're going to replace that with 12. Is 3.225. All right, let me write these down. Okay, first one was 0.1166. Second one was 0.1133. Third one was 0.4648. We'll round that up because the next digit was a 5. And then the third one was 3.2251. All right, let's take a look at how these exponential functions look graphically. So here I've got f of x equals 2 to the x and g of x equals 4 to the x. And what we see here are two curves that are pretty similar, but they do split up a little bit toward the end here as x gets larger. But the similarities show that over here on the left side of the graph, in the negatives, these are very, very close together, and they are increasing, but they're increasing very slowly until you get to the positive side of the graph for the x's, and then all of a sudden they kind of shoot up. Now this one, 4 to the x, we see rises much, much quicker than 2 to the x, but they both rise very, very quickly. And we've got a table of points to go along with that. So at x equals negative 3, the function's values are 1/8 and 1/64 for 2 to the x and 4 to the x respectively. For x equals negative 2, we find 1/4 and 1/16. Negative 1 is 1/2, 1/4. So these are some pretty small fractions here, pretty close together, but it isn't until at 0, they're 1, 1. It isn't until they're positive that we see the separation here. At x equals 1, 2 to the x is 2. At x equals 1, 4 to the x is 4. And then look at the separation here. When x is 2, 2 to the x is 4, and 4 to the x is 16. So quite a big bit of difference between the two at that point. Now, we're also going to look at something with an e here. E is an irrational number. E is actually the limit, and I know we haven't talked about limits yet, but we'll get to that later in the course. E is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth. This ends up being roughly 2.718 and so forth. And this has its own exponential function. So instead of 2 to the x or 4 to the x, this is e to the x. And because it's got its own function, we give it its own name. This is the natural exponential function. And the thing about the natural exponential function is Desmos, or many calculators, recognize what e is without you having to define what it is. So here I've got 4 more examples that we're just going to plug into the calculator. E to the power of x, where x is going to be negative 2, 0.25, negative 0.4, and 2/3. So I'm going to bring my calculator back over and show you how to plug those in. Now again, the calculator recognizes what e is. So when I just type e, it will automatically put in there 2.718 and so forth. So now I do e to the, and then for the first one, I'm going to replace the x with negative 2. And I get 0.1353. Okay, let's do e to the 0.25. And that'll be 1.284. E to the third one is negative 0.4. Gives me 0.67. And then e to the 2/3. All right, this is 1.9477. So you can plug these in just like you do the other ones, only this time the base of your exponent is just going to be e rather than maybe 2 or 4 or some other number. So I'm going to move this over and let's write down those answers. So the first one I had 1.353. Oh no, I'm sorry, 0.1353. The second one is 1.284. The third one is 0.67. And the last one here, 1.9477. Now in your assignment, you may be asked to round to the nearest 10th or 100th or maybe even 1000th. This is just kind of rounding to, I don't know, whatever number I felt like going to here. But keep in mind, you may be asked for your assignment to round to a certain value. Make sure you do that. So what are some real-world applications? One real-world application of exponential growth is how interest works. As an example, we're going to look at compound interest. This is when, for example, you put money into an account, like put money into the bank, and the way that that works is over time, that money is going to accrue interest, meaning that if you don't touch that money at all, you just leave it in the bank, you will end up getting more money year after year after year. So let's say, suppose the principal amount P is invested at an annual interest rate R, and N represents the number of times the account is compounded per year for T years. Then the value of an account A is as follows. So here are 2 important formulas that you should have written down in your notes. After T years, the balance A in an account with principal P and annual interest rate R in decimal form is given by the following formulas. For n compoundings per year, A equals P times the quantity 1 plus R over N. This is to the power NT. Now, if you see something that says continuous or continuously, that's going to be the second option. For continuous compounding, A equals P times E to the RT, often referred to just as PERT. So let's do an example of each. A total of $9,000 is invested at an annual interest rate of 2.5% compounded annually. Find the balance after 5 years. Okay, so let's find what these things mean first. P is the principal. That means how much did you start with? Well, the account started with $9,000. R is the interest rate as a decimal. You can do this by doing 2.5 divided by 100 because this is 2.5%. Percent is out of 100%. So 2.5%, 2.5 divided by 100 is 0.025. Another way of thinking of this is just moving the decimal point to the left 2 digits. So instead of 2.5, moving it over 2 spots, that's 0.025. Okay, N is how many times it's compounded per year. It just says it's compounded annually, so that's going to be once. If it said it was compounded quarterly, quarters, there's 4 quarters in a year, then N would be 4. If it said monthly, it'd be 12. If it said daily, it'd be 365. So be really careful with this number here for N. And how much time? We are waiting 5 years to see how much money is in that account. So T equals 5. All right, well, let's plug some stuff in. A equals P times the quantity 1 plus R over N to the NT. So I will say A is equal to 9,000 is the principal amount times the quantity 1 plus R is 0.025 over 1. And this is all to the 1 times 5. Okay, let's clean this up a little bit here. A equals 9,000 times 1 plus 0.025 divided by 1. So that's just going to be 0.025. So this will be 1.025. And 1 times 5 up here is 5. A equals. Let's plug that into a calculator. So I've got 9,000 times the quantity, 1.025 to the power of 5. This is 10,182.67. All right, that means that if you start with $9,000 in this account and you just let it sit for 5 years and you don't let it do anything to it, you don't take any money out and you don't add any more money, after 5 years, had you just forgotten about it and then you remembered 5 years later, you could take out all of the money that's there and you'd have an extra $1,182.67. Okay, what about compounded continuously? This last example, I've got a total of $7,500 invested at an annual interest rate of 3.25%, compounded continuously. There's that word. So when you see continuously, you're going to switch gears and you're going to use A equals P times E to the RT, or PERT. Find the account balance after 8 years. So in this case, P equals 7,500. R as a decimal, remember 3.25%, you're going to do this divided by 100 or move the decimal point to the left 2 spots. This will be 0.0325. And then T is 8 years. So A equals P times E to the RT. That's going to be A equals 7,500 E to the 0.0325 times 8. A equals 7,500. E to the 0.0325 times 8 is 0.26. Now I'm ready to put that into a calculator. 7,500 times e to the 0.26 is 9,726.975, or we'll round that up to 98. So that is $9,726.98. Meaning, if you start with $7,500 and you put it into this account, you let it sit for 8 years and you don't touch it at all, you can pick it up after 8 years and you'll have $9,726.98 instead. Hopefully this helps you out with exponential functions and their graphs, as well as a real-world example of how this is actually used.